Hi, everyone. My name is Sean O'Brien. I'm the Chief Technologist for Artificial Intelligence Analytics and Autonomous Solutions at Northrop Grumman. And I'm going to talk about the rise of artificial intelligence engineering, or AI engineering, today. So over about the next 40 minutes or so. So let me go ahead and share my screen. Okay. There we go. All right. So here we are, the rise of AI engineering and implications, of course, for geospatial science and related disciplines, which is, of course, why we're here today. So first, just a couple of things about Northrop Grumman, where I'm from. It's a very large defense and national security company. We do all sorts of things from undersea to space, as they say. We do cyber security. We create things like the B-2 bomber, the next generation space telescope, I guess now called the James Webb Space Telescope. And you can see, like in the middle of this image, that black and white airplane. That's a very, very large robotic drone. And all sorts of things, like we also do a lot of analytics, artificial intelligence, and things like that. So, and that's kind of my background, is that last part. So let's get started. Rise of artificial intelligence. So people like to ask, well, okay, so what's really different here in the last several years that's made artificial intelligence really explode in utility and popularity? It's winding its way into every aspect of our society, and it's really changing, every market and everything that humans do in pretty much every field of endeavor. And so where did that come from? Because artificial intelligence, in terms of the mathematics and a lot of the theory, has been around since the middle of the 20th century. Machine learning, things like that has been studied since the 1960s and to some extent even implemented. But in the last decade or so, and especially the last half of the last decade, it's really exploded. And it comes about because of these several technologies that have come into play over the last several years. One is just the continuing march of Moore's law, which essentially has been going since the 1950s. About every couple of years or so, the processing power and storage capabilities of computers have doubled. In the recent years, that has shifted a little bit away from getting more transistors on a chip into getting more chips into parallel processing systems. We also have the internet, which has connected all the data together from all around the world and enabled the creation of these truth data sets that can be used to train artificial intelligence algorithms. And cloud-based processing and data storage has been an enormous enabler for artificial intelligence, because it not only enables us to relatively cheaply access vast computing and storage resources, but it also makes those resources scalable, both up and down, which means if you're just a little startup company and you only need a little bit of storage or a little bit of processing power, you don't have to buy your own computers. You can just go rent them from one of the big cloud providers and rent however much processing space you need, and start out small. And then as your business grows, you can scale up. And this has really helped to spur a lot of the creativity that's come out of Silicon Valley and others. And the cloud-based processing and storage is now becoming very popular for government operations, of course. Deep learning algorithms is the final piece of the puzzle, and that is really advances in the science of artificial intelligence over the last few years. The creation of these deep neural networks, which are modeled on the structure of the human brain to some extent. And these are the first, real, true, robust learning systems that actually you can feed data into them. They will learn about the data and then go look for similar patterns out in the world. All right, so the current state of artificial intelligence algorithms, and I'm going to focus a little bit here on deep learning algorithms, these algorithms that are really good at within a very specified area of a mission, optimize the processes of a computer to do image recognition, natural language processing, or what have you. Um, it can play structured games now with at least with relatively straightforward rules in constrained environments, games like chess and Go and StarCraft and others. And they can do predictive analytics where the algorithms are learning from the real world what normal is and then learning to predict what's going to come next. All right, so the challenge comes in, and this is really where at the heart of the motivation for this talk and where we're headed with all of this is that these neural networks and other artificial intelligence technologies, they remain brittle and to some extent limited. They require very large training data sets that are all labeled meticulously to say this is really what a cat looks like, so go look for cats, etc. They're not really explainable or trustworthy. So quite often they're essentially a black box. And if it gives the wrong answer once in a while, even the people who created the system can't necessarily tell you why it got the answer wrong that time or why it's behaving in the way that it is. They're shallow with a limited capacity for transfer between domains. So if you train artificial intelligence on one set of data and then you go and try to apply it to something with a very different kinds of data, even though the algorithm is essentially the same, it's not going to necessarily do very well. They don't easily integrate prior knowledge. So there's a vast amount of human knowledge that has been acquired over the centuries in various areas, and being able to easily instantiate that knowledge into these systems is difficult. And it's difficult to engineer them into missionized systems. So this is a particular area of interest of mine because as we look to do more and more complex things with artificial intelligence, we find that there are gaps between what's readily available in the commercial world and what we really need in order to solve very complex problems for instance, for my customers. So though these deep learning solutions, they do become more precisely optimized as more data are fed to them, they don't yet really learn, at least not the way humans do. All right, so challenges facing AI teams. There's a mismatch between expectations, requirements, and technologies. The data are often ill-conditioned, they're inconsistent, they're not optimized for algorithms, and that's a really important one there. Pretty much every sensor that's ever been created by the hand of humanity was really optimized in order to present pictures and images and graphs and charts to human eyeballs. They weren't really, in most cases, created to present data to algorithms. And so things that might be very simple for a human to recognize in an image, these algorithms don't necessarily recognize them easily, and that creates problems. So there's also bad data, poor algorithm engineering processes, and also, frankly, general hype that damages trust in these systems. The systems are not generally designed for ongoing AI operations, and teams in the end then often rely on hope and zeal in order to succeed. All right. So AI engineering, the creation of AI systems using AI science, data science, deep learning algorithms, data sets that come from whatever sensors that you have at hand, that sort of thing. These need to not just be created, but engineered. And right now, the way the system works these days, in most cases, is that data scientists, computer scientists, mathematicians are generally drafted to engineer AI systems. Okay, the roles are often poorly defined and very widely. These folks are often poorly integrated into the larger engineering team. They're given non-standard tools, and the return on investment is poorly understood, so they lack consistent resources. Now, sometimes you get software engineers and you train them up as data scientists, and so that you kind of get the best of both worlds. But they're two different disciplines. And so that's a very inefficient way to create AI systems, to simply take software engineers who are good at software engineering and then teach them everything they need to know about data science, which is a very different thing, and then say, okay, go create AI systems. So data science is also still seen by decision makers as this kind of fairy dust. They can just, come bring me your AI and sprinkle it on my system, and so it'll work better, right? And that creates problems as well. So data science is still often treated as a subset or kind of software engineering by the people creating these real systems, rather than as a separate discipline with different process requirements. And as I've mentioned before, it's applied as a black box rather than holistically within the context of understood phenomenologies, targets, sensors, backgrounds, confusers, that sort of thing. All right, so does this sound familiar? We've got a new technology. It's growing in power and impact, and demand is exploding. Your engineering practices predate the new technology. Engineers have to be experts in both the old field and the new field. Current practices don't really address some of the new challenges that come with this new technology. And systems, therefore, are breaking more, they're behaving badly, and they're breaking budgets and schedules when you try to create these things. And therefore, because of all this, mistrust is growing. So what I'm describing, among other things, is the great software crisis of 1967, which is in many ways analogous to the situation we're in today with artificial intelligence. You know, all these things that applied that we see today with artificial intelligence versus software, the newly minted software engineers of 1967 were dealing with respect to hardware at the time. So this was a big problem back then. Computers were starting to become incredibly common. Not yet personal computers, but for a lot of engineering purposes. And originally, it was all about the hardware. But more and more of the efforts were started to be, put into creating the software for these systems. And eventually, right around this time, the software part of the system became more complex in many cases than the hardware. And yet all the processes of software engineering at the time had really just been lifted from hardware. Most of the people doing computer programming back then were electrical engineers. They had degrees in electrical engineering because they had grown up in the field to create computers, and that was mostly seen as an electrical thing. So in 1968, NATO held a conference in Garmisch, Germany, and they used a provocative title for the conference, Software Engineering, which was a new idea at the time. And the goal was really to abstract computer software from computer hardware. And this had begun a few years before when, with the rise of new computer programming languages like Fortran. Prior to the rise of Fortran and similar languages in the late 50s, in order to program a computer, you had to understand in great detail the exact way that computer was constructed. You had to be an expert on that specific computer and then use that knowledge in order to write your computer code, which was mostly written in literal zeros and ones, in order to make the computer do something. And so with Fortran, you suddenly could write code that could be used, taken from computer to computer, and you didn't need to necessarily understand the inner workings of the computer, of the hardware, in order to program the computer. You could write a program using the logic of the language, and then it would run on pretty much any modern computer at the time. So, but that was part of the solution. But still, all of the processes for creating these programs had come from hardware engineering. And there were a lot of specific problems that software engineers at the time had that really went beyond the processes that were available from hardware engineering. And so because of that, and the consensus that came out of this conference was that, well, complexity and expense of software was now rivaling and in fact, sometimes exceeding that of hardware. The hardware was becoming more commodity. They could no longer predict the cost and ultimate reliability of the software. So many software systems were never finished and they just failed. Others came in vastly over budget and way beyond the schedule that had been placed because they just didn't know how to predict how long it would take to write a complex computer program. And this was because the software had unique problems that just weren't taken into account in the processes that had been created to develop hardware systems. So, and even when the problems were analogous, they really needed to be tailored for software. So finally, and this is really important, they came up with this idea that the engineers really should be focusing on one thing, So why did they have to be electrical engineers first before they became software engineers? Couldn't they just focus on learning software engineering and be software engineers and leave the electrical engineering and the creation of the computer to the hardware engineers? It sounds like an obvious thing now, but that was a revolutionary idea at the time, that abstraction and division of labor between the hardware and software. So all of those ideas really apply, I believe, to where we are with artificial intelligence right now. Our new idea in this case isn't software engineering, it's AI engineering, and our goal is really to abstract AI from computer software. And when I say this, quite often people will raise their hand and say, "Well, hold on, but AI is code, AI is software," and that's true. But most of the software that AI sits on top of is not really relevant in a deep sense to the AI. There should be a way, and we should be seeking a way to abstract that so that someone who's writing the AI code in whatever form that is, perhaps using one of the new languages like Python or R or what have you, they shouldn't have to worry about all the details of the underlying software. Why do they have to be software engineers before they can be AI engineers? And I don't think they should have to. But getting there is going to require us to hide a lot of those software engineering details from the AI engineers so they don't have to worry about them. In the same way that Fortran hid all of the details of the hardware engineering of a computer from the software engineers. So that's what we're kind of after. And as I just mentioned, Python and R and those languages, which really aren't that new, of course, those are starting to move us in that direction where they have already begun to hide some of those details so that the AI engineers can focus more on the AI and less on the details of being, software engineers. But that's only part of the way, and there's a lot more that needs to be done. We are, again, finding, just as they did in 1968 with software engineering, that the complexity and expense of AI is now oftentimes rivaling or increasingly commodity software, that software layer underlying that. We can no longer predict the cost and ultimate reliability of many AI systems. AI has unique problems compared with software. And as we'll see in a moment, this has caused the Department of Defense, for instance, and other entities around the world to come out with new principles which speak to engineering for the construction of AI, that they've had to add to the principles that were used before to oversee the creation of software systems. I'll talk about more about that in a moment. And even where the problems are analogous, they need to be tailored to artificial intelligence. We have these modern software processes like, say, DevOps, continuous integration, continuous delivery, these kinds of concepts. And we're now trying to use those to deliver artificial intelligence, but those processes were created with software engineers in mind. If you give the DevOps manual to an artificial intelligence engineer or a data scientist, they may not be able to make heads or tails of it because they're not necessarily software engineers. So, and we'd like them to be able to focus on one thing. Why must they be software engineers first? Okay, so AI engineering concepts, really three I'd like to focus on here. One is abstraction that I've been talking about already. Specialization. Non-software engineers should be able to directly engineer AI systems without having to get a 4-year degree in software engineering first. Extensibility. AI systems should be able to be deployed directly across different software systems. Right? Modularity and power. So the complex AI systems can then be built directly from AI component subsystems to solve harder problems, but with the same science. In other words, with this kind of modularity, and this is something that the rise of microservices and containerization of software is helping with as well. You can solve more complex problems without pushing back the boundaries of artificial intelligence science, right? With the underlying mathematics and science of artificial intelligence, by adding AI systems of systems, and building these things one after another, taking a bunch of different AI parts and pieces and creating something more complex that can solve a more complex problem without needing to invent new science. Finally, simplicity and robustness. AI systems can, in this case, with be tested and operated on their own merits, separate from the underlying software and hardware. And this was, again, analogous to that situation in 1968. They wanted to be able to test and evaluate the software without having to worry about the hardware. Separate those two problems out, and we're trying to do the same thing here. We're trying to separate out the problems of artificial intelligence, the robustness of it, the reliability of it, the trace problems, without necessarily having to worry about whether the underlying software layers are operating correctly. That should be a separate issue. All right, so this gets to kind of the heart of AI engineering, the foundational concept, I'd say, of artificial intelligence engineering, which is that unlike traditional software, the behavior of AI systems is determined by, one, AI models. These are the algorithmic code that operates on and from the data. And two, the AI data themselves. So the data that are used to train the models, to test the models, and to operate the AI system. The data that flow through the system as it's operating out in the real world. Those data sets help determine how the system behaves. So it's not just the code. And in fact, I have a friend who's a data scientist, working on some very complex problems. And she says that her software testers, since they've started using artificial intelligence algorithms, her software testers don't know how to do their jobs anymore, because they're used to doing these tests every week, and maybe there'll be updates on, to the code. And if there are, then you want to test and make sure that those updates didn't break the code and change its behavior too much. But what they're now finding with artificial intelligence systems is that the behavior of the system can change even when the code hasn't changed at all, simply because it's learning from the data that are continue to flow through it. And so code hasn't changed at all, different answers. And that the software testers were not trained to deal with that problem. So the duality of code, the fact that or the duality of AI systems, means that the code alone is no longer deterministic of the behavior of the system. And so to really understand the system and the way it operates, you have to engineer both the algorithms and the data together and consider those to be integral parts of the whole AI system. It's not just code anymore. It's code plus data. And so that relationship between the models, the AI algorithms, and the code must be tracked continuously in a robust system to ensure that robustness, not just to ensure robustness, but also to prevent cognitive drift. In other words, we've trained it on one set of data and now we have it out in the world, but the real world data is maybe drifting away from the characteristics of the training data that we used, or maybe from the test data that we used. Maybe we need new test data. So in order to do that, we have to maintain a provenance, a map back in time, the relationships between the codes and the model. So this particular AI model was trained by this particular data set, and we have to keep track of that as the system's life cycle evolves. And that also implies the criticality of a DevOps approach, right, which comes from software, but now must be tailored to AI. All right. So Department of Defense has responded with these AI ethics principles, they call it AI principles. They were announced a year ago, February 2020, by Secretary of Defense Esper and Lieutenant General Shanahan, who was then the director of the Department of Defense Joint AI Center, the JAIC. You can look them up. I have a link there and just Google them, ai.mil, ethical principles for AI. And basically they come out of the idea that the principles the DoD has long operated under are no longer sufficient to deal with all of the problems of artificial intelligence. They were sufficient, generally speaking, to deal with the problems of software and hardware, but artificial intelligence is different. And so they needed these new ideas. And so they proclaimed that DoD systems must from now on be AI systems created responsibly. They must be equitable. They must be traceable. So you have to be able to trace back why they behaved, why their behavior was a certain way. Where did that come from? Where in the system was that behavior determined? They must be reliable, of course, and they must be governable. How do we make sure that the behavior of the system stays within the bounds we want them to maintain? So these sound kind of like policy questions, but they represent fundamental engineering challenges as well. And that's what I want to talk about. So where do we go from here with AI engineering? Well, we want to move from data that have to be pure and clean and structured to being able to deal with messy and unstructured data. We want our AI models to not only have to be supervised, where we have, which means all these very, very carefully labeled truth data that are used to train them, to be able to have them just send them out into the world and learn from the world without us telling them what's what. They learn what's what on their own. Unsupervised learning, that's called. We want our processes to evolve from software-centric to data-centric, right? We want to focus on the data and the AI models and not have to worry so much about the software underlying it. The phenomenologies we're dealing with, we want to move from a target-only focus to a holistic understanding of the system, right? So if you're trying to train your system to recognize cats and cat videos, say, you want to understand, you could do better, your algorithms will do better if they have a contextual understanding of the world. And this is something that we're seeing a lot of in research right now, where, if you take a human child who's 18 months old, they don't learn to recognize cats by looking at 100,000 pictures of cats that are labeled cat. That's not how they do it. They do it with a lot less data than that. And why is that? And that's partly because when an 18-month-old sees a cat, there on the kitchen floor, they recognize that is an object in 3 dimensions that is in a larger 3-dimensional world. And so when they see it from a different angle, they understand that this is the same object, but it's seen from a different angle. Early and a lot of current AI algorithms don't have that context. And so providing that kind of context, having that holistic understanding of the situation, can make our AI more robust and also traceable and reliable and all those things that DoD wants. We want to move from sensors that are human-centric to sensors that were created with algorithms in mind. Okay, and I'll talk a little bit about that with some real-world examples in a little bit. And we want our capability to go from just minimum viable to being truly mission-enabling. Right? Okay, so missionizing artificial intelligence for, in my case, Department of Defense and intelligence community missions, things like geospatial analysis. That requires that AI systems have well-conditioned data, that existing systems are created to deliver, and I mentioned that existing systems were mostly, created for human operators. We need them to take into account artificial intelligence operators as well. Our algorithms, these algorithms have different requirements than the humans do. And that leads to the need for robust data engineering, which is one of the sub-concepts of artificial intelligence engineering, right? If artificial intelligence is made up of models and algorithms and data, then artificial intelligence engineering is going to be about the engineering of algorithms, algorithmic engineering, and data engineering. Those are the two main components of artificial intelligence engineering. Intuition, context, and experience of the world need to be included somehow. Right? We need to give them that context. They must be able to take advantage of existing human knowledge and subject matter experts. They must be explainable, capable of describing the reason the AI, made the decisions it made to a human being. And that's not just important to create trust in the end user, like, oh, why did this thing do that? It's also critical for engineering the system so that the engineers, when they see the thing starting to behave a different way, they can trace that back to some factor within the system, and they use that to better engineer the system. And finally, collaboration is key. The mission subject matter experts, the analysts, the operators should be able to experiment with AI hypotheses and models without having to be experts in data science themselves. All right, so AI engineering, AI systems engineering in this case, it's a multidisciplinary field, especially right now when the abstraction of AI from software is not anywhere near complete. So if you really want to create a robust AI system, you need mission domain knowledge. You need people who understand the things you're trying to find, the sensors you're using to find them, the platforms those sensors live on, how they operate, and the concept of operations, the ConOps of the mission. You need data scientists who understand the machine learning and the statistics, visualization, classification, that sort of thing. You need, quite often signal processing, sort of, old-fashioned pre-AI algorithms, right? That come from physics, that come from phenomenology, that have to do with, reducing noise, things like that. And then on the bottom here, we still need software engineering to make sure these things scale and are optimized, and high performance computing and high efficiency computing to make sure that they operate within the bounds that we need them to in terms of processing time. So, bridging the gap from data science to missionized AI systems requires that we change our practices. So here I list a bunch of challenges: algorithm engineering, data engineering, I mentioned those, but then some specific things that often trip up AI systems, like false positives, staff skill sets that are mismatched, scalability of the system, test and evaluation is a huge one, and user experience. And you can see common practices there in the middle. Use the use of canned data science algorithms, like, okay, here's the algorithm. I downloaded it from the internet. Let's go ahead and use it. Black box data conditioning. So, well, this is the way the data are delivered by the sensor. So, okay, that's what it is. And test and evaluation in particular is a really important one, because right now, a lot of the test and evaluation, it's still seen in many development systems as a hurdle you jump through at the end of development. And once it's tested and evaluated, you're done with that and you can go on to operating. Well, with AI systems, because they're non-deterministic and evolutionary, test and evaluation needs to be built in from the very beginning. And you need these test harnesses that can pull telemetry from inside the system, from various points in the system, in order to tell how the different parts of it are operating, so you can trace its behavior. Especially if you have an AI system of systems, where maybe you have neural nets that are feeding decision trees, that are feeding other neural nets, et cetera, to solve complex problems. So we need new tools and new techniques. So I'll give an example of this kind of an idea: how to find a needle in a haystack. So many commercial AI applications have historically ignored the false positive problem. If you're trying to, suggest sneakers of a certain type to people, false positives aren't necessarily critical. But if you're trying to do something more complex where people's lives are at stake, then false positives can be an issue. So, clean data means that things are easily separable. And in the commercial world, that's often the case. And if that's not the case, you move on to a different problem that you can quickly monetize. That's what the commercial world's about, right? But if you're doing like a national security mission, then the mission is the mission. You can't just pick another one because the AI didn't work that well. So most government missions have very strict false positive requirements, right? You don't want it to say something is a car if it's not a car. And they have ugly data, right? So target and false positive populations now overlap. Their characteristics are similar, right? And the false positives can carry a very serious mission impact. So what I show here on the bottom is, on the x-axis, you see those two Gaussian curves there on the lower left, the blue one and the orange one. You have a population of confusers, things you don't care about, and a population of targets that you want to be able to find. And I've drawn a threshold, a green line there through the middle of them, and that's basically whatever you're using to measure these that something is a target or not. It might be its size or its shape or something like that. And of course, this is a cartoon, and that's not how like a neural net works, but it's a way to assess whether or not your thing is operating correctly. So if you take that threshold, that measure that you're using to determine yes target or no false positive, and you move that back and forth, you can make sure you're getting rid of more and more false alarms, but you also start to eat into your target populations, missing more and more targets, right? So you can plot these. If you plot the detection probability on the y-axis and the false positive rate on the x-axis here, you can create this what's called a receiver operator characteristic, or an operator curve, and that's that curve on the right. And depending on where you put that green bar, more to the left or more to the right, you get an operating point that allows you to tune whether or not whether you care more about getting rid of false alarms, or whether you care more about making sure you don't miss targets. And if your system is very, very carefully tuned and clean and not very noisy, then that curve tends to shift upward and to the left. And so your operating curve can, your operating point can do a good job of getting rid of false alarms without losing a lot of time. Okay. So, but often what we find is that if you want to find the needle in the haystack, it's better to study the hay. And that's where we get into these complex AI systems of systems. So what I've shown on the top here is a situation where, you have very overlapping false positive population and target population. And, the way most artificial intelligence systems try to improve that situation is by improving your target model. And if you do that, and if the populations are well separated, then you can actually end up with that situation on the upper middle here, where you've separated them out by narrowing your target population by tuning your detector. And now you can put that green bar in between them, and you've got all the confusers on the left, false positives or potential false positives, and you've got your targets on the right, and they're cleanly separated. And look, we can operate right here where our detection probability is nearly 1 and our false positive rate is nearly 0. Great, right? Okay, well, what if the target and false positive populations are not well separated? That's the middle graph here. Well, now if you only improve your target model, then there's nowhere you can operate where you're not going to have a large false positive rate, right? The only way to get rid of the false positive rate is to move this threshold so far up that you're missing all your targets. And so you end up with a operating curve that looks like this one in the middle. And even, if you try to put the operating point on this curve where the detection probability is high, the false positive rate is also high. So how do you solve that? Well, if you take a system of systems approach, you can start saying, well, let's put, this is again a simple case. Let's create a neural network to, or another algorithm that focuses on various false positive populations in this blue curve here, right? And if you can do that, then you get the situation on the bottom, right, where we start out with these two highly overlapping populations. And we refine a model of our target, and sure enough, here's our narrow little target population. But if we then create some detectors that are focused on the false positive, then we can narrow that population as well and get back to a situation where we can operate at a point that separates those two. And we get back to here where we're operating at a very high detection probability and a very low false positive rate. And we did that without improving the AI science, without getting better neural nets or whatever comes after neural nets, but instead by using, a AI system of systems where we use multiple neural nets, each focused on a different aspect of the problem in order to solve it. And of course, in the real world, it's even more complex than that, and you have many different populations. And you think, well, if I had just a super, super good data science, mathematical algorithm, then it would just automatically do all that itself. And that's true. But until we have that, we can, as engineers, use the tools we have today that data science gives us today, and we can solve more complex problems by creating more complex systems, right? The same way that software engineers do, and the same way that hardware engineers do, by creating more complex hardware systems to solve more complex problems or more complex software systems. You can do the same thing with AI. So to solve this problem, we might have many AI modules that operate together in concert to solve a more complex problem. Okay, so the value proposition here is really combining our data science, our algorithm engineering, our software engineering, our powerful proven processes and mission domain knowledge, our high performance computing, our cloud computing to create missionized artificial intelligence, to create more effective and efficient platforms, sensors, et cetera. So this is what one of those system of systems might look like, okay? We have input data, a module for that. We have a module for reformatting the data, a module for conditioning the data. We do background mitigation, where maybe we filter out some background things even before we do entity detection, the kind of detection things we're trying to look for. And then maybe we ensemble them. Maybe we take many different detections, and we ensemble them in order to create Uber detections, or look for patterns of activity, not just maybe where things are in the world or what they are, but what they're doing. And then classification of those things. Is it a car, a cat, a dog, a camel, what have you? And then that all then goes into reports and training and testing models, et cetera. But the thing I'd like to point out here is that every single box you see here might include one or more artificial intelligence algorithms or systems in its own right. Okay. It's an artificial intelligence system of systems. And that rides on top of the underlying software system, the underlying hardware system that it's built within. So, and I'll pick another sort of cartoon example, the idea of battlefield situational awareness. So let's say you're trying to figure out what's going on, in a complex environment like a battlefield. Well, you could think of this as like a stairway of understanding, right? We start with perception at the lower left, which is just really organized sensor information. Maybe it's just a whole bunch of dots on a map, like you see in a classic radar, image, where here are all the dots, in X and Y coordinates, lat long. So that's just your basic perception. But then that could be feeding another layer of artificial intelligence that takes the output of the perception layer and now says, well, what are all those dots doing? What are their kinematics? What, are they doing things that are normal, weird? Can I take what they're doing and then feed that to another layer to tell me what the situation is going to be in a little while? So we go from perception, where everything is, to to situational awareness, what the situation is. In other words, what are the kinematics? What are the activities that are going on? Then we can use that to feed into the next layer, which does predictive awareness, predictive analytics. Given what's going on now, what's going to happen next? That leads us to situational understanding. Why is the situation the way it is? And we build more and more context and more higher levels, more abstract levels of understanding. And each of those layers will have one or more artificial intelligence modules, each being fed by the one before it and feeding the one after it. Okay. This is an engineering problem, but it's not a software engineering problem, at least not in the traditional sense. It's an artificial intelligence engineering problem. Okay. So how do we do that? Let's take that example. We're trying to detect anomalies in real time using full motion video and wide area motion imagery data feeds. So these are essentially video feeds. Wide area motion imagery is sort of FMV, but at a higher level. So instead of just having like a high definition or a 4K video system, you've got many of those all stitched together into this giant God's eye view, where you could surveil an entire city all at once at sub-meter resolution, maybe 30 kilometers or on a side, and you're getting updates of 1 or 2 per second. So you're looking at everything, hundreds of thousands of objects moving all around all at once. So those cameras exist. You can get them commercially, but it's too much data for humans to look at. So how do we deal with that? So this is an example of one. And I'll show you some real videos from this. This is a system that delivers 25K by 25K, 25,000 by 25,000 pixels per frame at 1 to 2 frames per second. And we got some test data that Wright-Patterson Air Force Base published a while back. That's publicly available, just for people to play around with and test their algorithms on. Each box in this image represents a high definition TV monitor. That's how much data we're talking about here, and it's over that 25 by 25 kilometer display. That's far too much data for a single human being to understand in real time or otherwise, really. So we take a pattern of activity approach to anomaly detection. So unlike some threat activities where you can predefine them, so we're going to look for swarming boat attacks, or we're going to look for some kind of specific thing. In this case, we're using artificial intelligence to look for things that are just different. So instead of, again, studying the needle, we are going to study the hay, and we're going to just teach our algorithms to detect things that are not hay, detect things that are not normal patterns of behavior in the traffic. So this is an unsupervised machine learning algorithm. Right? It's not previously trained on prior data. It trains as it goes on what's going on in the world. So this is what we're talking about. In this case, the The green dots are actual traffic. This is real data from the real world, near Wright-Patterson Air Force Base. And all the objects, detected were detected and tracked in this case by the Northrop Grumman team. And then we set them loose with our AI algorithms to look for patterns in them. So here's what it looks like, and it's ugly. It's a multi-camera system, so you can see the seams in between. The reason they all rotate around is because what's really happening is an airplane is flying around in a circle, kind of orbiting this area. And then when you map it flat to lat long on the ground, it looks like the camera's rotating around, or the camera seams are rotating around. And you can see the traffic moving around on there. This is relatively low resolution, so we're trying to understand cars and what they're doing and everything, but there are only 2 or 3 pixels on each target. And there are all these funny seams and contrast differences, and this is an awful data set for an algorithm. So in this case, showing an example of, that started again. There we go. In this case, this is a traffic activity where we took and we actually injected an activity, which is easy to do in something like this because it's just kinematic, which was a person pulling off to the side of the road in a place where that doesn't normally happen. And you can see the algorithms finding it, and the team that was writing the algorithms was not aware of what was being put into the data, so it was blind from their standpoint. But the algorithms easily picked up that red dot there where a car had pulled off to the side of the road where no cars normally did that. And the algorithm learned what was normal just from the green behaviors that were in the data themselves. So with basically no prior training data. Here's another one where we looking at a compact convoy of cars going along the freeway. And in this case, again, the algorithms picked that out very quickly, saying with only a few minutes of looking at the real world, it was able to say, oh, well, that's not normal for that area. Those cars are too close together, traveling all in a tight group. And again, but without previous understanding by the algorithm of this is what we're looking for. Just this is different, and here it is. That's very powerful. And it's what you can do when you create these AI systems of systems that focus on understanding the context, not just, hey, let's see if we can figure out what cars look like. So that's pretty much it. I wanted to give you an example to go over what you can do with AI systems of systems when you apply these AI engineering processes that we're starting to develop at Northrop Grumman and elsewhere in order to try to abstract AI from the underlying problems of software and hardware. So I've listed here just to tie everything together, these sort of 10 principles of artificial intelligence system design that we've developed here, just to guide us in thinking about these things, right? Starting with the idea that AI is not fairy dust. You don't just add it to a system, it's core to the system, and often it defines the overall system function. The sensors and platforms should, when possible, be designed to optimize to serve the AI, not the other way around. That the artificial intelligence, has a dual nature consisting of your algorithmic architecture, your models, and the data that are used to train, test, and operate those models. Test and evaluation has to be continuous. It needs to be automated, and it needs to instrument the code, the models, the data, and the end users if possible, so that those end users can provide feedback on what works, what success looks like. AI traceability and governance rely on understanding of the interrelationships between the code, the models, and the data. Systems development is a multidisciplinary engineering challenge. Right? We need to, especially right now where AI has not yet been fully abstracted from software, we need to have software engineers and AI engineers and working sitting shoulder to shoulder as they develop these things. And it's important to understand that algorithm engineering, data engineering, software engineering, these are all different but complementary disciplines. So we shouldn't assume that one set of processes is going to work for everybody. Data science and machine learning do not by themselves provide complete solutions to problems, right? Again, it's an engineering task. It's not just about data science. You have to make these things operational. AI models generally require much cleaner data sets than humans, and therefore data engineering is often the most challenging aspect of AI systems development. And then finally, AI usability. It's a human-machine team, so user experience requirements should be factored in. So that's pretty much it. I hope that I've given you some useful information on this, what we think is an emerging field of artificial intelligence engineering that is going to increasingly abstract AI from the underlying field of software engineering that it came from, software engineering and data science. And I think it's a very exciting time, and I'm really looking forward to the future and seeing where this new field goes and what it's going to be capable of. And it's going to be very interesting to see how this new engineering field can take artificial intelligence to new heights, hand in hand with advancing AI science and data science. So thank you very much. I appreciate it, and I hope you have a great day, everyone. And I will end there.